Hello, my name is Matt Miller, and this is Lab 5, Choose Your Own Adventure Lab for Physics 2211. So just an introduction about what I'll be doing in this lab. I will focus on observing an inelastic collision and how we might use observational data to estimate the coefficient of restitution between a dropped object and its surface. I will use Tracker to observe the motion and then use GlowScript to construct a computational model in which we will test different values to align the computational with the observed data. So, for the procedure of the observation, I'll just use a camera to record a video of an object being dropped from rest from a certain height and observe its motion all the way through its complete motion. I will then use GlowScript to code a computational model in which we can add a coefficient of restitution and test values until the observed is similar to the computed. So some background information. I chose to use Newton's second law to update the ball's initial and final velocities as well as positions and net forces on the system. The coefficient of restitution comes into play and is defined as the ratio of the final velocity to the initial velocity between two objects after their collision. And so you can also find this by taking the square root of the ratio of the heights that the ball achieves after each bounce, but we will use the initial velocities. And some initial information: the ball's mass that I used was 0.0349 kilograms, and the initial position vector is given to be that, and it was dropped from rest, so the initial velocity is 0. So here is the tracker data. As you can see, the ball was dropped from a certain height, and I observed the motion through all complete bounces and collected the X and Y data through time. We will use the fundamental principle of Newton's second law to determine the position, velocity, and net forces acting on our object. F equals ma. For this lab, we will only consider the force of gravity acting upon our object. We will just neglect drag force. So the change in position is noted as velocity times change in time, and change in velocity is F net divided by mass times change in time. And so here's the code for my computational model. We just initialized it with the ball's mass, ball's position vector, and ball's velocity vector. We also put in the CR, the coefficient of restitution, and we will talk a little more about that in a minute. So in my while loop, I included an if statement to achieve the ball's bounce. If the ball's position equals 0, then we will negate the ball's velocity. So that's when the ball hits the ground, then the velocity will be negated. The F grav vector is just equal to the ball's mass times gravity, and the F net equals the F grav. And the ball's velocity and ball's position equations are given based upon Newton's second law, and then the different energies, the kinetic and gravitational energies, are defined as such. And so we coded this in order to import a CSV file from our tracker data, and we will plot those two sets of data on the same graph when we run our code. So here's what that code looks like. The blue ball is the computational model, and the red ball is the observed data. So we imported our data from tracker and ran the model, and you can see how each of those compared in the graph. So as you can see, the observed data closely resembles the computational model, only in such that it doesn't achieve the same heights, but the times at which the ball hits the ground are very similar. So this is a good model. Now we'll talk about the coefficient of restitution. As you can see, as previously stated, you can derive that by taking the square root of the ratio of the heights achieved by each bounces. And you can see that in each bounce, it's roughly about half the initial height that it was dropped from, or it reduces by 1/2. So if you take the square root of 0.5, that's equal to 0.707, which is close, and I came to conclude that 0.75 matched the closest, was closest to match up the two sets of data. So what does the coefficient of restitution say about a collision? The coefficient of restitution will depend on what two objects are interacting with one another and how they will store energy. When a soft object strikes a harder object, most of the energy available for the post-collision velocity will be stored in the soft object. So this coefficient of restitution will depend on how efficient that object, the soft object, is at storing the energy in compression without losing heat or plastic deformation. So, for example, a rubber ball will bounce better off concrete than a glass ball. So in conclusion, this lab is a simple way of understanding an inelastic collision in the real world and how it can help us make better judgments about what two objects might interact after a collision.